So that's great. We've learned how to write expressions for the equilibrium constant. How do we get an actual number for this? Well, the most direct way is to let the equilibrium establish itself and then measure the concentrations of everything and stick them into the expression. So here we've got our H2 plus I2 reaction, and we are given equilibrium concentrations. So we're supposed to calculate Kc, equilibrium constant in terms of concentration. So we're going to write the equilibrium constant expression. So we've got Hi squared divided by concentration of H2 and concentration of I2, right? There's no solids or liquids in this one. And then we're just going to take these numbers and plug them in. So for Hi, we've got 0.78, and that's squared, and that's divided by 0.11 and 0.11. I'm getting 50.3, 50.28. And, you know, just being reasonable with the sig figs, we'll call that 50 of the decimal point. No units on an equilibrium constant. I just want to mention this dividing by these two things here. This is the same as, you can rewrite it this way. I can pull out 1 over 0.11. This is 0.78 squared divided by 0.11 divided by 0.11. A lot of students want to multiply them down there, and that's fine if you use parentheses, but otherwise you end up being off. So you can do it this way, and you need parentheses 0.11 times 0.11. So make sure your calculator is giving you the correct answer, because it's just really sad to do all the complicated stuff correctly and then have this one little glitch on the calculator and get the wrong answer. It's still the wrong answer, though. Okay, any questions? So again, with that hydrogen and iodine reaction, so we can calculate the equilibrium constant, right, by looking at the concentrations at equilibrium. And so what we've got here are several different little experiments where we started with different starting amounts. So here we've got equal amounts of H and I and no product to start with. This is the one we just did. We calculated it and we got an equilibrium constant of 50. What if we start with only product, 0.5 moles of HI, and let that go to equilibrium? Stick those into the expression, we get 50. What if we start all three of them equal? You can do any combination you want. Let it go to equilibrium, plug it in, you get the same number. That's why it's called an equilibrium constant, right? Because it's constant, it doesn't change. It is important to specify temperature, though. So this is specifying at 445, and I'm not going to try to trick you with that, but when you see a temperature listed there, don't freak out and think that you have to incorporate it into your calculation. It's just sort of the small print. This is at 445. Any questions? We can also calculate the equilibrium constant if we know what the initial concentrations are and we know what one equilibrium concentration is. This is much more realistic, because when you've got a mixture of things, it's not too hard to measure the concentration of one thing. It's kind of challenging to measure the concentrations of everything at the same time. So here we're going to look at a very simple equation. A is decomposing to form 2B. And so we're going to set up a little table like this where we list the initial concentrations, the change in concentration, and the equilibrium concentration. And those initials, ICE, spell the word ice, and so that's why this is often called an ice table. It's also sometimes referred to as a rice table if you put the reaction up here, but the book calls it ice, and rice makes me hungry, so we'll just stick with ice. So here we've got initial concentration, 1 mole per liter of A, and we're starting out with none of B. At equilibrium, we are told, because it was measured, that the concentration of A is 0.75. So we can figure out the other things. So if this was 1 and now it's 0.75, how did it change? It decreased by 2.5, right? So we'll go minus, I'm sorry, 0.25. Yes. Decreased by 0.25, right? It is just that simple. So if that one went down, then the product must have gone up. Now here we have to be a little bit careful, right? Because there's a coefficient involved here. For every 1 mole of A that goes away, I form 2 moles of B, right? So if I lost 0.25 moles of A, how many moles of B did I gain? 0.5, right? Times 2. So this is, well, we could do it this way. This is minus 2 times 0.25. I'm sorry, plus. It's a plus, yes. Plus 2 times 0.25. And this 2 is from the coefficient. So if we started at 0 and we gained 2 times 0.25, that means I've got 0.50 molar B at equilibrium. Now I know the concentrations of all the reactants and products. I can plug those into the equilibrium expression and calculate the constant. So Kc for this is going to be the concentration of B squared divided by the concentration of A. So I put my numbers in. I've got 0.50 squared divided by 0.75. I get 0.33 repeating. Any questions? What does the overall magnitude of that equilibrium constant tell us about this reaction? Does it favor the reactants, the products, or is it kind of in the middle? It favors the reactants a little bit. But remember, with equilibrium constants, some of them are like 10 to the plus 30, and some of them are 10 to the minus 30. So on that scale, 0.33 is pretty balanced. It's pretty close to 1. So it favors the reactants a little bit, but there's significant amounts of both. So let's do one that's a little more interesting. So the reaction shown between carbon monoxide and hydrogen is carried out with the initial concentrations given. At equilibrium, the methanol concentration is 0.11 molar. Find the equilibrium constant. So we're going to make an ice table. And I'm just going to use the equation at the top. That's why they sometimes put an R up there for rice. So I want initial, change, and equilibrium. So the initial concentrations were given to me. Carbon monoxide was 0.27. Hydrogen is 0.49. They didn't say anything about the product. 0. It is usual that when you have a reaction occur, you put the reactants in there and you don't add some of the products, because if you're adding product, why would you be doing it if you already had the products, right? So if it doesn't mention a concentration of the products, you can assume it's 0. You should assume it's 0. Now, we're told at equilibrium that that product concentration is 0.11. So we're going to look at the methanol, the CH3OH. It started at 0, and it went to 0.11. So what was the change? It increased by 0.11, right? So now we need to look and see, well, how do these other things change when this changes? So what's the mole ratio between carbon monoxide and the methanol? It's 1:1, right? So if I lose 1 mole of CO, I gain 1 mole of that. I gained 0.11 moles, and so that tells me I lost 0.11 mole of the CO. You see how I did that? Now this one, the hydrogen, we need to think about this a little bit because this has a 2. And so you could get mixed up. You could say, well, you could multiply by 2 or divide by 2. Which is it? Well, stop and think about it. If I react 1 mole of this, I react how many moles of that? 2. So I need to take the change of CO and multiply it by this coefficient because it's going to use twice as many moles per liter of hydrogen. So this is going to be minus 0.22. This same change, but multiplied by 2. Everybody okay with that? Okay, so now we have some simple math to deal with here. So 0.49 minus 0.22 should be 0.27. Well, that's not exactly on the line, is it? 0.27. And then over here we should have 0.16. Is that right? I did that in my head. It's dangerous. Okay, so then we write our equilibrium constant expression. We've got CH3OH, divided by CO and H2 squared. You should always write the equilibrium constant expression and then put the numbers in. Don't just go straight to the numbers. So now we'll put the numbers in. I've got 0.11 on top, 0.16, and 0.27 squared. Looking in the wrong place, 0.11 divided by 0.16 divided by 0.27 squared. 9.43? Any questions? It's very important to understand how this ice table works because things are going to get more complicated and we're going to use them a lot. So if you have any questions now, you should ask. Let's do another one. Reaction shown is carried out with initial concentration of CH4 is 0.087 at equilibrium. H2 is 0.012. Find the equilibrium constant. So again, we're going to make an ice table. Initial, change, equilibrium. Initial concentration of the methane was 0.087. What about the other ones? 0. Those are products, and it's not mentioned, so we can assume that those are 0. We're given an equilibrium concentration for the hydrogen of 0.012. So In a problem like this, you're given initial concentrations and the equilibrium concentration of one thing, and that's enough. So how did the hydrogen change? Well, it went from 0 to 0.012, so that's a change of positive 0.012. We could figure out what the change for the C2H2 must be. We're using the change in the hydrogen and the stoichiometry. So 1 mole of C2H2 comes with 3 moles of H2. So this is creating 1/3 as much as that, right? So this is going to be an increase of 1/3 times 0.012. Everybody okay with that? Our reactant is going to be decreasing, so it'll be negative. And again, we need to take into account the stoichiometry. So for every 3 moles of H2, we lose 2 moles of CH4. So we've got something times that 0.012, right? Sometimes it's easier to think, well, what if that was, let's make it a nice, what if this was 12? What if the change for the hydrogen was 12? So we could say 12 moles per liter of the hydrogen, and we could put in a mole ratio here. There's 3 moles of hydrogen for every 2 moles of CH4, right? Now, this is moles per liter, but these moles cancel out. And so what we're doing is we're changing molarity of hydrogen into molarity of methane. So 24 divided by 3, that comes out to be, what, 8? So you're going to use these coefficients to, in those changes. It's easy to get them upside down. So if you have to write something out or put some simple numbers in there to make it easier to think about, go ahead and do that. That's why I was saying, well, if this was 1, then that would be 3. If this was 1, that would be 3, and that would be 2. And so those are our ratios. So this tells me I'm going to take 2/3 times the 0.012, and this is going to be negative. So my change for the H2, C2H2 gives me an ending concentration of 0.004 and 0.087 minus 2/3 of 0.012. I'm getting 0.079. So we found our concentrations. We're going to write out the equilibrium constant expression, H2 squared, CH4. That's not squared, it's cubed. This one's squared, and this one's on the top. Oh, sorry, this is a little backwards. With all the, with all these lines in here, I'm just not really seeing my arrows very well. It's these two on top. This one's cubed, this one's just single, and CH4 on the bottom. So I've got 0.004, 0.012 cubed, and 0.079 squared. got 1.1 times 10 to the minus 6. Anybody else? I might have screwed that up. You got 10 to the minus 8? Okay. You got 10 to the minus 4. Okay, so we have 3 different answers. This is awesome. I'm going to do mine again. 0.004 times 0.012 to the 3rd power divided by 0.079 squared. I got the same answer. 1, 2, 3, 4, 5, 6. 1.1 times 10 to the minus 6.
Yeah, I got the same as you.
Okay. So, it's easy to screw that up. Now, I'm using the raise it to the power button and the squared button on my calculator, and occasionally you wonder, well, am I using those correctly? And so you can always just do it the slow way and multiply by 0.012 3 times and double check that you're doing it okay. And then divide by 0.079 and divide by 0.079. Yeah, I stand by my answer. So those of you that disagreed, were you able to convince your calculator? No? Okay.